All right, hello everyone. I'll let everyone get settled in here. My name is Ray McLendon, and this is Leah Berg, my colleague. We're with Data Science Rebalanced, and we both happen to be two data scientists at the Kansas City Federal Reserve. When we first started working at the Federal Reserve together, we kind of bonded over the fact that we felt like our sort of schooling, our education, didn't fully prepare us for our data science careers. And so what we decided to do was put something together, education-wise, in Data Science Rebalanced to help bridge that gap from going from an academic setting into the industry setting from a data science perspective. That being said, we are Federal Reserve employees. Hopefully this will move for me. Maybe not. Oh, need to move back up. Yeah. So whenever we talk, we have to come with this lovely disclaimer stating that everything we say is our opinion and doesn't represent the Federal Reserve, the system, the Kansas City, or the Board of Governors. You know, don't want to freak out the stock market. So, with that said, we'll dive into our actual workshop, which is Feature Engineering is for Everyone. And we'll cover a couple of things here real quick. So, a quick intro to features, and then we'll kind of break the world down into two different spaces, discrete data and continuous data sets. And from there, we'll basically talk about exploring those data sets versus creating them. Here are the tools that we'll be using along the way, some Colab, pandas, and so forth. So let's dig in. Introduction, what in the world is a feature? Some of you probably have a good feel for this already. A numerical representation of some form of raw data is how, I guess, Webster might put it. For us, being data scientists, we often use it as an input into our machine learning models, but it can also be used for data analysis or data analytics, automation, quality, and such. What we're really going to aim for is creating features, so the feature engineering process, which includes creating them and selecting them. I'll be frank, we don't have enough time today to really get to the selection part. We're mostly just going to cover creating them for today. So, talk over some quick use cases. Data analytics, I mentioned earlier. So, I think if you were to take a course in like BI and data analytics, they would probably never use the word feature in the entire time that you're in that course. But a number of the items that you're using are technically features. They are numerical representations, and then you're just making visualizations with them. Another example, I used to work in the renewable energy space with wind energy and Internet of Things. You have sensors out in the field. Sometimes they go bad. You can use features to help you determine when your sensors are going bad. We work in the Federal Reserve banking system, and so whenever we want to use machine learning, we have to have interpretable models. Now, there's some really cool deep learning stuff that's available, but generally speaking, that's not allowed as much in the banking space because you have to be able to interpret why you're, let's for instance, denying someone credit. So, simpler models, we're back to using features. So, for the, apologize, break up. I'll switch over to Leah for the next part.
No, you're good. All right, guys, so we're gonna head over to Colab. Hopefully, you guys got our message ahead of time and were able to access the Colab notebook. You should be seeing something that looks like this. Yes. Yeah, we can zoom. Actually, you know what? Maybe let me. Here we go. Okay. Does anyone not have the notebook? If not, not a big deal. I do have the link for it here in case anyone does need it. So I'll flash that here for a second in case anyone needs that. Okay. I'm going to move this out of the way. Okay, and so first off, we're going to just do a quick intro to Google Colab. If you haven't used this tool before, it's a really nice tool. It's really great for presenters like us because what it allows us to do is just focus on the content and not worrying about getting Python installed on your machine or setting up a IDE or anything like that. So this all runs in the cloud, which is really awesome, and this is where we're going to be doing our coding today. So I'll just give a quick little tour here. Over on the left-hand side, we've got this little hamburger-looking menu that gives us this table of contents. What we've tried to do throughout this workbook is make it so that it's really easy to navigate. We've got these headers so that you can jump around in there. We've also included a lot of extra detail that Ray's going to be covering in the slides, hopefully so that you can use this really as a standalone notebook moving forward and not have to bounce between slides and code. So we've got our table of contents. If you need to find and replace, that's available. We're not going to really be doing that today. Over here, we're going to have some variables. If you've ever coded in an IDE before or a development environment, you normally have a section where you can see all your variables and what the type of them are and all that good stuff. So that's there in case we need to look at that. And then last thing I'll touch on over here is this folder icon. So what you should be seeing right now is this sample data, and maybe if you've stepped ahead a couple of steps, you might be seeing your own Google Drive. That's where we're going to get to, is connecting up your Google Drive to this instance of Colab so that it can reference the data set we're going to work with today. Okay, so I think that wraps up our Colab intro. I'm going to toss it back to Ray so that he can talk to us about exploring discrete data.
Okay. So exploring discrete data, this probably isn't going to take a crazy amount of time per se. So first off, what in the world is discrete data? Our simplistic way of putting it is it's data that can be represented by the natural numbers or whole numbers, 1, 2, 3 through n, however you like. And some examples are number of employees in your department, or number of customers acquired this month. Oop, no worries. Product categories, sentiment analysis, positive, negative, neutral, that can be represented as just 3, discrete. And in our case, with a lot of the work that we do, unstructured text. So we'll have a fair amount of examples around that because that's what we use on a regular basis. So how might we explore this type of data set? There's basic summary statistics, the kind of stuff you would have learned back in school, mean, median, mode, yada, yada. There's also bar charts, which we're going to definitely do some of. Line charts, especially if you're wanting to see how your discrete data is changing over time. And then there's comparisons. So if we have a couple of columns of discrete data, we might want to compare the behavior between two sets. Again, we deal with a lot of text, so I figured I'd just have fun and throw up an example real quick. In this example of doing a comparison, it's between two documents, document 1 and document 2. The combined documents we refer to as our corpus. It's all of our documents together. And the vocabulary down below is the unique set of words, or if you want to be picky, tokens, that exist in the entire corpus. And so what we can do here is we can actually represent each document as kind of like this word count of how often each word in the vocabulary appears. And that becomes a way in which we can compare just these kind of discrete pieces of data in terms of documents. So we'll dive into more of that later. So with that, I'll switch back over.
Sounds good. Okay, so we are going to get into our Google Colab notebook. Hopefully you all got that up and running. What we need to do first is make sure you're connected to a runtime up in this top right corner. Just make sure you see basically what I'm showing here, this green check mark, and you're good for that. I should also say a couple logistics things. Anytime you guys have questions, feel free to stop us and we'll answer those. And we've got what we're going to do in these is first, Ray's going to talk through all the slides for us, give us the conceptual understanding. Then we're going to do an example through it in Colab. And then we have several exercises for you guys to actually do on your own. So that'll be just kind of the way that we run down on things here. Okay, so with that, let's get started. So first off, we just have to do a tiny bit of setup. What you'll do in your notebook is if you haven't already, click on that This Link button And I can even zoom in a little bit more here. So you'll want to click on that. What we need to do here is get the data set that we're going to work with for this first section. And what we're going to do here is, instead of having us all on the conference Wi-Fi download a like 200 meg data set each, we're going to just point to where it's stored on our Google Drive, ours being mine and Ray's Google Drive. So what you'll do if you haven't done this already is just click on 2023, and you're going to do add shortcut to drive. So that is going to make a copy of that over into, well, not a copy, but just a link out to it inside of your Google Drive. So once you do that, and there's a picture there, if you need those instructions again, you should be able to go ahead and click the play button on that first cell here. It might ask you just to give permission and make sure that it's okay that it's connecting to the drive, and then you might have to select your account over here as well. So I'm going to select the one that I'm using today. And then it's just asking to make sure that it's okay that it connects, and I'm going to say allow. And once we do that, it should give us a little like green check here saying that we're all good to go. So I'll wait for that to show up. Okay, we've got our check. And to double check that this actually worked, what we can do is click on that folder icon on the left-hand side, and you should now see a drive option. And if you click into that, you should see a My Drive, and then under that, that's actually all of your Google Drive. But what we've done is create that shortcut to our 2023 folder that has the data set in it. So everyone good on that step so far? Okay, well, no problem. We can wait just a second. Good?
Okay.
Awesome. Okay, so I'm gonna minimize that so it doesn't take up half of my screen. So we're gonna actually get into exploring discrete data. If you guys wanna go ahead and run that next cell there under the exploring discrete data header, what we're gonna use is a library called Pandas. If you haven't used this one before, very popular library for data science. It allows you to manipulate data and do a lot of analysis. A really nice library. So we're going to use Pandas to load in our CSV data set, and this data set that we're working with is all about technology product reviews. So you can imagine anytime someone buys a product online, maybe that's a new laptop, maybe that's a new camera, anything like that, they might write a review for it in publications like CNET, or I think another one from this data set is TechRadar. Lots of publications out there, but they'll give their opinion on what their thoughts on the product is, and that's the data set we're going to be using. So mainly unstructured text is what we're going to be working with today. Now, to explore this data, a really nice tool that we like using is a library called Wide Data Profiling. And if you haven't used that before, you might know of it under another name. It used to be called Pandas Profiling, but this is a really handy library that allows you to generate a bunch of charts and a bunch of insights on your data set. So if you want to go ahead and run that next cell there, what we're going to do is install the Wide Data Profiling library into our environment. I should have mentioned earlier that in Colab, it comes with a lot of built-in libraries for us, but this is one that does not come with it, so we just have to pip install that. And similar syntax to, like, if you're using a Jupyter notebook, that exclamation point is just saying, let's run it in the terminal. So we'll let that install. And once we get that installed, the next thing we'll do is actually create the report. And I'm going to go ahead and run that. You guys can go ahead and do that too. It'll take it a second. What we've done actually is just take a sample of the data set so that it runs a little bit faster. We're just picking up the 500 random rows in our data set. This random state parameter is just saying, let's initialize on a certain point so that we all get the same data points to work with. If you don't want to see the same data points that I'm seeing, you can change that number if you like. Yeah. Oh, so sometimes it might, oh, you're talking about here. Don't worry about that. It's talking about like matplotlib and some other stuff, so we should be good to not restart. Good catch though, thank you. Okay. So what this does is we've actually saved this report off into an HTML file. So we should be able to see like somewhere over in, yes, our documents over here that we have this. So if you wanted to, you could open it up in the browser. I'm just displaying it inside of our cell here. But what's really nice about this is it gives us a whole bunch of charts and insights into our data, like I mentioned earlier. And I'm actually not going to go through it too much because that's going to be an exercise for you guys to explore the report itself. But you can see at the top here, we've got just a bunch of headers for giving you an intro to what all it has to offer, but a lot there to explore for every variable that's in our data set, and an easy way to do that. I would say before we knew about this library, Ray and I wrote a whole bunch of like custom code to basically do all of this. So we were really happy when we found this library, really useful one. So I'm gonna, again, let you guys explore that here in a second, but before we do that, we're going to talk through histograms, which are a type of bar chart that Ray mentioned. So for this next section here, what we're gonna do is explore the titles of our reviews. So these are the title of those articles that people have written on the technology product reviews. What we're going to do actually here is see how many tokens or words are in a title on average. If you want to go ahead and run that cell, we will get a histogram that we can talk through. First, I'll talk through the code here just so we understand what's going on here. And again, stop me if anything's not making sense or you've got questions or anything, happy to answer those. So a couple things here, don't worry too much about this warning stuff and the pandas options. That's me just setting some things to make sure the workshop goes well. But to do this plot, we're gonna use a library called matplotlib. So I'm importing that. And then what we're going to plot, like I mentioned, is the number of words or tokens, as they're called in natural language processing, that are in the title of our articles. So when we do this plot down here, on our x-axis, we get number of tokens that are in a title. So we're ranging all the way from like 2 tokens up to 26 tokens or words in a title. And then these are the number of articles that had that amount in them. So this is another way to explore a data set. The wide data profiling library doesn't give us this out of the box, so it's a really great starting point for some analysis, but as you kind of start exploring data, you'll naturally have more questions that you might want to answer. So this was one of those for us, and that's how we did that there. And with that, I think we're ready for you guys to actually code. So what we're gonna do here is we're gonna have about 10 minutes to explore that wide data profiling library and the results of that. We will have you guys create a new column in the data set that counts the number of words that are in the article. So in our example, we were looking at the title. We just want to do the same thing, but on the article itself. So we've got, I think, some helper text in there to help you guys out on this. I will say, what we're going to do here is I'm just going to stop talking and you guys are going to go for 10 minutes and explore, do all the exercise there. We would like to really encourage pair programming. So if you've got a neighbor next to you that you know or one that you don't know, good opportunity to meet people. And if you're having any challenges or anything, feel free to reach out to them. Ray and I will also be circling the room at that time as well to help out there too. Any questions before we get going? Okay. So with that, I'm gonna start a 10-minute timer. So let me just get that ready. Okay, and I'm gonna go ahead and start. So you got 10 minutes to work on that. Okay, so we are back from our 10-minute exercise. A quick thumbs up, thumbs down on how that went for you guys. Okay, cool, seeing mostly thumbs up, that's awesome. So I'm just gonna go through our way that we did this. Most of this is just copying the code from earlier, so shouldn't be too much to explain here. So first off, what we wanted you guys to do was create a new column in the data frame that calculates the number of words that are in the article, so the text of the article. So we did this earlier, we just had it on a different column, so should have just copied that code there and changed that column name that you're referencing to article. So not too tricky there. I'll go ahead and run that on mine, and I will run this one as well. So then what we wanted you to do was just explore the profile report and all that it has to offer. And I heard a lot of you saying that you liked using this library, maybe a first time for a lot of you. It's fairly new to us as well, and we've found a lot of benefit out of it. So really recommend that library. But while that is loading, actually let me go up to the sample version and I'll just talk through it a little bit. So at the top here, we just have some navigation for all of the things that the library offers. You start off with an overview of your data set, which is really nice, seeing how many rows are in your data set, if there are any duplicates in your data, what's missing, all that good stuff. You also get some nice alerts. So all of these ones that have high cardinality, that's just saying that there's a lot of distinct values or unique values in that column of your data set. So this is a nice way to just get a quick overview of that data set. And then if you ever need to reproduce this analysis, it does have a nice section here that tells you what version it was on, as well as just this JSON file with all the settings that were used to produce this report. Which in the data science space, reproducibility is super, super critical. So nice that it has that. And I won't go in too much because hopefully you guys had enough time to explore on your own. But the nice thing about this library is that for each column in your data set, what it does is it gives you some more information about that column, as well as a quick bar chart. You can also use this library with time series data as well. We will do that later, so it can even do that. You can click on like more details, and it has a lot of stuff for text as well. So like, what are the most popular values in the data set? What are the most popular characters? I use this a lot to check for data quality issues myself, just making sure that the field is showing what I would expect it to. So really powerful there. There's also a section on interactions. Kind of similar to correlations. This doesn't really make sense for this data set because we only have one field that it can do the interactions on. We'll get a better understanding later in our data set. We've got correlations, which not really relevant for our data set. Could be seeing like what the correlation is between the publication that the article was published in versus the score that it was given. Might be useful for us in our analysis, might not. And then there's a section down here that gives you where you're missing data. I don't think we're missing any data in this data set. And finally, you get a sample of the data set. So this would be like if you printed out like a df.head on your data set or tail, it just shows you what the data looks like, which is probably useful since you guys haven't seen this before, but I've seen it several times. Yeah?
Would it run a lot slower if we didn't do the 500? Like, is that a best practice? Just give it sample data and we'll give it all.
Yeah, so the question was, would it run a lot slower if we did not do just the 500 sample? And yes, it would. That was why I actually scrolled up to this one because mine was still running. I did mine on the entire data set. It does take a little while, and it also takes a lot of RAM. We've run into some issues where, especially in this Colab notebook, we'll run out of memory when we're trying to work with these things. So bigger your data set, yeah, unfortunately, the slower it does run. But there are a lot of settings you can set on it to limit some of the things that it's doing in the background. Like you can cut out the correlations and other things like that so that it's not having to compare every single column against every other single column. So yeah, there's ways you can limit it, but in general, yeah, it does run slower. Okay, so I am gonna pass it back to Ray, and he's going to talk us through how to create features. We just went through exploring, and he's gonna go through creating now.
Alrighty. So creating features for your discrete data set, and I think I warned ahead of time there will be a very strong NLP bent to it because that's what we do on a regular basis. So the first one that we'll talk about is one-hot encoding, as it's referred to. It ends up being really useful as an input to machine learning models. So if you're going to build out a machine learning model and like you have a sort of a set of discrete publications as an example this time around, and you want that to be an input into your machine learning model, one-hot encoding is the way to go. What you'll see here is that we have essentially 3 distinct publications listed here. I think your data set actually has 4. But because we're showing 3 here, The length of our vector or array, however you like it, is a length of 3. And then each position is associated with a specific publication. And it's purely binary, yes or no. So Tech Radar is our first one. It shows up as a 1 in the 1 position. PC Mag is in the 2nd position. And then CNET is in the 3rd one. And as you can see in the 4th example, it's CNET again, so it's in that 3rd spot. If you were doing a one-hot encoding for the data set, which we will be doing in a little bit, you would see that your array would actually have 4 instead of 3. It's just however many unique discrete points you have in your data, in your column of data. So that's one-hot encoding. So on the flip side, if we're looking at the output of a machine learning model, and we're expecting it to be a discrete form of data, we would classically call that classification. That output, we would actually encode that using what we call as a label encoder. And so if we have, in this case, let's see, 4 distinct product categories, car, computer, audio, and mobile, then it's simply going to just produce a 1 for the first one, 2 for the second one, 3 for audio, and then mobile gets set to 4. So 1 through n, basically. It's just doing that quick little switch so that we have a numerical representation of our data set. And so label encoding, the big key point is that we generally use it for what we call the target value, the output of a machine learning model, whereas the one-hot encoding is for the input. That's a great question. I'm not sure that I know why it starts at 1 versus 0.
I don't know.
I've just always seen it start at 1, but I don't know that there's a reason it has to. Yeah. No. Okay, so I mentioned the text bent. Here we go. So in order to lay this out, I'll start off by sharing this basic concept of like text similarity. So earlier we were talking about documents and how we might compare them. Similarity is the way to go about it. There are 2 sort of basic ways of thinking about it: lexical similarity versus semantic similarity. In lexical similarity, you're looking at the literal words. So 2 documents, if we say they're very similar to each other from a lexical perspective, it means that they share the exact same words. Whereas semantic similarity is meaning that they share the same meaning. So even though the words may not be the same, they're still talking about the exact same thing. So 2 different types of similarity. And you'll see that we will work with different features that handle each type. Oh, pointing the wrong way.
Oh, sorry, my thing.
No, you're good. Yeah, that'll work. Okay, good stuff. Okay, so some quick use cases. One would be for removing duplicates. I've worked in a number of places where databases may have duplications in them that shouldn't be there. You can use similarity to root some of that out. Recommending stuff to people, especially when you're in the world of text. Also, if you're dealing with students, plagiarism, perhaps. And then finally, there's a kind of connection going on between like the recommendation engine, search engine thing. But there's a lot of times where there's like lexical search, and then there's semantic search. So back to this example, hasn't really changed, except we're going to talk about a couple different ways of doing this. So the first one, which sets our foundation, I spoke through earlier, where this list in this column here is the unique set of words amongst all our documents, what we call our vocabulary. And then each column is for each one of the documents that's in our corpus. And it's just a word count, simple word count. So what this column represents is basically a vector, and that numerical representation for document 1. And the next column is the numerical representation of document 2. So similar to kind of like the one-hot encoding, you have a vector that has a certain length. These vectors would be the length of your vocabulary, the size of your vocabulary, and then it's just counting up how often each word appears. So we're going to get to doing some fun bar chart stuff, and you'll see things exactly like this. In fact, I think you will see exactly this one when you get there. And that's just actioning off of those word count vectors and allows us to be able to paint a picture of which words are most common in our data set. So actually, I'm going to bounce back really fast. There's an interesting issue that happens in this. So this is coming from our product data set, product reviews. It's not too crazy that the word that appears most often is use, because they're talking about their use of the product. That seems quite natural. Which also means that if I were to stick these word vectors into a machine learning model, it might actually overemphasize that word. So we want to clean that up, and that's essentially what the next technique gives us. TF-IDF, term frequency inverse document frequency. There's two core parts to it. There's think fractions, numerator, denominator. In the top is how many times did this word show up in the specific document I'm looking at. And in the denominator, what we're essentially looking at is how often did that same word appear in the entire corpus. So essentially, if the word shows up too often across all the documents, the denominator is going to grow big and squash the signal. It's going to compress it and say, we don't want to pay attention to this word because it shows up too much. It's not meaningful. So
it's basically like filler words, right? That you may just get rid of.
that's right. And there's actually a whole set of words that are like that called stop words in NLP. So the, it, of, if, these are just words that we just say, remove it all together. And we're going to use a library that will automatically remove those stop words. But use is not a stop word in most dictionaries. So whenever you're working in a specific industry, there will be certain words that that industry overuses, and TF-IDF helps squash that out. Cutting over, the first two that we talked about are in the lexical similarity space, and now we're touching on the semantic very, very briefly. So in this space, we have embeddings, and they're all the rage these days. We have word embeddings, sentence embeddings, document embeddings, all types of embeddings that handle different sizes of text, basically. So certain models, even if you were looking at GPT models, they can only handle so much stuff being shoved into them at a time. So this is just, when we say word embedding, it's meant to consume one word at a time versus something that's relatively the length of a sentence, basically. But what this does for us is it captures the meaning behind the words that are in this case, we're going to use a sentence embedding, as opposed to, and we'll show an example where we have two strings that they do not have any words in common, but they're talking about the same thing, and it matches them as being similar, somewhat similar to each other. So that's the nice part about this technique. Yeah. With that, I will cut it back to Leah.
Yeah. Okay, how the heck do we do this in Python? That's what we're going to learn next. Okay, let me get past all my exercises. Okay. Creating features for discrete data. So everything that Ray just talked about in the slides, we're going to do it in Python, and similar to last time, we're going to have some exercises for you guys to try it out yourself. I will say just another logistics thing. I'm going to run through the examples of how to do this stuff. Then we're going to go for a 15-minute break, so bio break, whatever you need to do then, and then we'll come back and you'll have time to do the exercise. Or I guess if you don't want to take a break, you can have extra time for the exercises. Okay, so what we're going to do here is first talk about how to do a one-hot encoding. You can imagine you probably could write this up yourself if you wanted to, but there's nice libraries that do this for us. One of the libraries that can do this for us is Pandas. It uses a function called getDummies, kind of a funny name, but it's creating a one-hot encoding for us. Don't know why they didn't call it one-hot encoding, but question for another day. So to create a one-hot encoding, you guys can go ahead and run that cell if you like. what we're doing is we have to pass in what data we want it to create a one-hot encoding on. In this example, we're passing in the publication, which I believe is what Ray had showed in the slides. So we're matching up there. We're saving that off as its own data frame and then doing a merge to merge that back onto our original data frame. If we didn't do that, we'd just have a data frame with like ones and zeros and that's it. But we kind of want to know what were the articles that was actually for, so that's why we're joining that back on to the original data set. And so we can see here, if we scroll over in our data set and scroll up as well, what that has done for us is create 4 new columns for us, one for each of the publications that we're working with, CNET, PCMag, TechRadar, and Trusted Reviews. And if we look over in our publication column, for example, this first row here, the publication was TechRadar. So what we do to create the one-hot encoding is that we put a 1 in that column. And likewise, I think if we scroll down to the bottom of the data set, we can just make sure that it's working. We've got some ones that are in that Trusted Review publication, and we get a 1 in that last column there. My scroll bars are messed up. Okay. So that's how you can create a one-hot encoding really easily. Any questions on that? Oh, yeah, so the question was, what's the left index, right index? That's me telling it how I want it to join. So behind the scenes in Pandas, actually I think right here for us, this first column here, that is our index. So it's basically like a row number. So we have the same in both of the data sets, so I'm saying that's the key that I want to join on between the two. So it's saying from the left data frame, use the index, from the right data frame, use the index, and that's what you join on. Good question. Any other questions? Okay, on to the next. So Ray mentioned that one-hot encodings, that's usually used for inputs into machine learning models. And on the flip side of that, we have label encodings, which are used for the target value or what we try to predict in machine learning models. And that's where we would use a label encoding. So you could also do this by hand if you wanted to, but there's a really nice library called scikit-learn, which is a very popular machine learning library that has a built-in label encoder for us. You guys can go ahead and run that cell, and then I'm gonna talk through what we're doing here. So first up, this line here, what I'm doing is importing the label encoder from scikit-learn. And then something I'm doing here is not necessary for making the label encoding. It's something that I need later on in the workshop, so we're just doing it here. Basically what I'm doing is just filtering down to the TechRadar publication. That's the syntax of how you do that in Pandas. If you haven't seen that too much before, just saying where publication equals TechRadar, and I'm saving that off as a new data frame called TechRadar-DF. And then from there, I'm taking a sample, again, not necessary for label encoding, but I need this later on in the workshop, so we're doing it now. So save that off as its own data frame called TechRadar sample, and then to actually do the label encoding, we have to initialize our label encoder, so that's what we're doing here, and I'm just calling it LE for shorthand. And from there, to do the label encoding, finally, what we do is call this fit transform function off of the label encoder. So what that's gonna do is look at our data that we're passing into it. In this case, we're passing in that category column from our sample data frame. And it takes a look at all of those and then assigns that 1 through n value, depending on how many categories we have in our data set. I'm saving that off as a new column called encoded category, so we can take a look at that here, and that's what we're gonna do with this TechRadar sample.head. That's gonna show the first 5 rows in our data set. And what we should see is we've got, after our one-hot encodings that we did, we have a new column called encoded category, and that gives us a number. So 1 through n, however many categories that we had, it assigns a value to those. So in this case, this category was mobile phones, and it gets an 8. Likewise, these next 2 were in the computing category, and those 2 get assigned a 5. So it looks like that's working correctly for us. Any questions on label encoding before I move on?
Why are we using one-hot encoding for the input while number encoding for the output, not vice versa?
Yeah, so the question was, why are we using one-hot encodings for inputs and label encodings for outputs? Ray, you wanna take a stab at that?
Yeah, I don't know that I have an amazing answer for that one. To be fair, it's essentially what I was taught is the way to go about it, doing it for machine learning purposes to get the best result out of it. So I'm not sure that I have a good breakdown as to why one is better than the other. I guess most of the classification models that I've seen use like a label encoder on the end of it. And that usually works really well, as opposed to trying to have it spit out an entire vector. I mean, it's already technically doing that. It's spitting out a vector with all the scores across every class. But yeah, I don't know that I have a perfect answer. Yes?
So maybe this is foreshadowing, but the fact that you're bothering to do a label encoding of the publication, are you trying to predict what the publication is based on something? I mean, why would you label something that you already have?
Yeah, so sometimes
Right.
we're just messing around to give an example, and also not to do the assignment part. In a use case that's been done with this data set before, you're actually predicting the product category based off of the review. And I have two hands.
I don't know if this is a question, but if you one-hot code something, there's no implied hierarchy. Whereas
Thank you.
When something is a sequence, 1, 2, 3, 4, it implies there's a relationship between 2 and 1.
That's true. Yeah, that's right.
And so that's why a lot of times in models will be more successful if you one-hot code.
Yep.
And then for categories, it's just kind of more convenient. You don't want to have a whole vector.
Yeah.
Keep a track of if something's a category.
Thank you so much.
I guess
No, that's a fantastic.
Great explanation.
Yeah.
You want to
Bad memory,
paraphrase
but
for
yeah,
the, since
100%.
they're not on the mic.
Oh, you're right. Yes. Thank you. Yeah, exactly. Wonderful audience member called out the fact that if you use label encoding 1 through n, it gives an association of hierarchy, ranking, so to speak, and that a one-hot encoding actually prevents that from happening. That's my summarization. Not as eloquently stated as you did. But yeah, that sounds dead straight in line.
Question?
Yes. I missed the very end.
I was just saying, I've never used this before. I thought it was like a type of emoji.
Yep. Gotcha. Any others? Oh, yes.
For the label encoder, how does it get the category 1 to n?
Yes, so during the, so it says fit transform. I'm stepping on your space. The fitting part that it's doing is basically going through and identifying how many unique items are in the field. So that establishes what the n is. So.
Can you define what 1 to n is instead of getting from the document?
Actually, you can, yes, because I've done that before. Except the situation where I did that, to be fair, was I wanted to, my data set always assigned a 1 through n, but I also wanted to account for the situation where we didn't know what the category was. So you can append extra labels onto it. That is possible. I have done that before. We don't have an example here, I'm sorry, but yeah.
Awesome. All right, so that was label encoding. Yeah, so scikit-learn makes that really easy for us and does all that code in the background for it, and we just have to call the 2 lines of code basically, which is really nice.
And then with the fit, can you just create a dictionary so you can encode it on the back end, right? Like you probably need a diction at the end, right?
Right, yeah, that was what Ray was mentioning, is that you do have an opportunity. Sometimes maybe your data set that you're working with doesn't have all the possibility of the categories that you're trying to encode. So that is a way you can do that, is to add those on and tell it about that data as well.
Yeah, and I guess the thing that I'd add is that this fit transform and then you encode, there is a function in scikit-learn to like reverse, to back out of it.
Right.
To say, okay, here's the number you gave me, give me back the actual category.
Yep.
That is in the library too.
Yep, yep. All right, so moving into text. Next up, what we're going to do is start simple. We're going to start with word count and then work our way up to the sentence embeddings that Ray was talking about. So for word counts, I've got like a whole big paragraph of text here. I'm going to try to summarize it for you so you don't have to read all of that. One of the nice things that scikit-learn also provides for us is something called count vectorizer, which basically does the word count for us. Like I've mentioned a couple times, you could definitely write this yourself if you wanted to, but why not reinvent the wheel? So let's use what we know and use our resources. So count vectorizer, we're going to be using that to do our word counts here, and then we're going to be using a library called Berg, which sits on top of scikit-learn and does some nice charts for us so that we don't have to write hundreds and hundreds of matplotlib code to do our plots. So we'll be using that one. It's called their frequency distribution visualizer. That's what we'll be using. So for this example, you guys can go ahead and run that cell if you want, if you haven't already. That's going to give us our plot, and I'll talk through the code here. So what we're doing here is we have to tell count vectorizer what do we want to count. In this case, we're going to use our sample data frame that we created earlier, just so it doesn't take as long to run and so that the chart isn't exploded. But we're going to plot the top words that are in the title of our articles, so our reviews that people have written about these technology products. So to do that, we have to define what is our corpus, which Ray was talking about earlier back in the slides. So in this case, we're saying the title column of that data set, that's going to be our corpus. I'm calling it variable corpus. And then from there, we're going to call count vectorizer, well, initialize it here. So count vectorizer has a ton of parameters on it. I think I linked up here to all of the things you can customize on it. We could go into all of those, but that's probably like its own natural language processing course. So I'm going to just talk about two main ones that are really useful. First one being stop words, which Ray got to earlier. Stealing a little bit of my thunder here. That's okay. So stop words, like he was mentioning earlier, are things that just aren't really important in the English language, or they get used so much, like they don't really add any value if you're trying to analyze text. Those are things like I, but, for, not, usually short words that get used a lot. So what we can do in scikit-learn, count vectorizer, which is really nice, is they have a built-in list of stop words for us. Every different library that you use, there's a lot out there that can do the same sort of thing. They each have their own list of stop words. It can be sometimes useful to combine those lists together, or sometimes, like Ray was mentioning earlier, even create your own custom list. Like for example, we work in the banking space, so words like bank, finance, those get used a lot, and they don't really add anything to our analysis, but they're not by definition just a regular stop word. So what we do a lot of times is create a custom list that we add on to the list of words that come out of count vectorizer. So that is one technique you can use. They also have this for many different languages. So you'll see we're here calling out the English language. So those are the list of stop words that I'm using. But you could do Spanish. I don't even know what other languages they have support for, a ton out there. So that's that first parameter. Second one here is called n-gram range. And this gets into a concept in natural language processing around something called n-grams. And it's basically like how many words at a time or chunks of like text at a time do you want to analyze. So something that's called a 1 gram or a unigram would just be one word at a time. So we're just going to take one single word at a time, which is actually what we're doing here, and that's what's in our chart. When we print that out, you'll see we just have one word here, so we're printing out unigrams. What we could do if we wanted to change this is we could do something like bigrams, which would be taking 2 words at a time. So you could, if you want even, just change those 1s to 2s, rerun that cell, and then we should get a chart that shows us 2 words at a time. So this is really nice. You can start to see like what phrases are people talking about in our data set. This is a powerful technique for exploring the data, but also for creating features for the data, which we're on the creating features section, but just wanted to highlight it as good for exploring as well. So you can go up to any number that you want there. It would likely decrease the chart the higher numbers you go, because there's probably less common phrases that people are using across all of the articles in our data set. But I'm going to flip this back to just unigrams. Oh, I should also mention that if you wanted to show unigrams and bigrams, so one word and two word at the same time, that's how you would do that here. It's a range, so you could put any numbers you want there. I'm gonna flip it back to unigrams, and that kind of goes through the two important parameters for count vectorizer that we want to talk through. So that's us just initializing it. Then, to actually apply it to our data set, we're going to use that fit transform function that we learned about earlier. So it takes a look at all of our data and then does the transformation of the counts based on what we're passing in. So we're passing in all the titles of our articles, so saving that off as this docs variable. And then for the plot, to get the words to show up here, we just have to use this function, get feature names out. That pulls out that list of words so that we can actually interpret this chart correctly. So we have all that, and then from there we pass that into our frequency distribution visualizer from Yellowbrick, setting a few parameters on there. You can print how many tokens or words you want to show at a time. I'm just doing 20. You could change that if you want to see more than that, and then we just have to fit that on our data set and then do a show there. So all that to say, we get this nice chart here of our word counts. And Ray kind of went into this a little bit earlier, but he mentioned that sometimes some of these words that get used, like in this example, review, is in almost every title, which makes sense because it's people reviewing technology products. So if we were going deeper in this course, probably what we would want to do is remove that from our data set, because that doesn't really add any value. We know all of our data set is reviews, so just get rid of that from the data set. But we're not going to actually do that today, but just wanted to highlight in case further exploration. Okay, any questions on word count so far? Yeah.
These are raw frequencies, not normalized by document, right?
Correct. Yes, they are raw frequencies.
Could I do the same thing just by a single group by? So if I understand correctly, the point is every label on the left corresponds to a vector, but it's just not showing.
Yeah, well, so what it's doing behind the scenes is literally going through every piece of our text here and counting up how many times do I see this word. So that's what we get there. And you were asking about, could you do that with a group by, I think. I think you could. We would have to finagle the data a little bit more. So we, in this example, just passed in the title itself. If we wanted to do a group by, we would probably need to split that out into a list or get our data prepped in a certain way for us to do that. So this just makes it a little bit easier for us to do. Yeah. Any other questions on word count before we go to TF-IDF? Okay. Okay. So on to TF-IDF. So we remember word counts, those, like this gentleman in the front mentioned, are just those raw counts. So what we get is, like how we saw earlier, review shows up a lot, but if we were to pass just these word counts into a machine learning model, it might look at review and try to make decisions off of that, which we don't really want that to happen. So one technique to improve on that is TF-IDF, or term frequency inverse document frequency, that Ray talked us through earlier. So we're going to just go through how to do that on our data set. Scikit-learn to the rescue again has a built-in method for us called TF-IDF vectorizer. So we're just importing that. We have to, again, define what we're going to pass into TF-IDF. So what do we want it to count up for us and normalize? In this case, we're going to do the title of our articles again. And one quirk about TF-IDF is it expects a list of those values. So I'm just formatting that data set as a list there. So we get that. And then from there, we have to initialize TF-IDF. We're using those same two parameters. It has a lot more. Those are the only two we're going to cover today. So again, getting rid of those English stop words, things like of, but, for, stuff like that. And then we are, for this example, only going to go with unigrams. But you could change those values if you want to 2, 3, whatever number you like. Yes, there's a question.
You created a corpus underscore list,
Uh-huh.
but I don't see where you use it.
Oh, you are so right. that is a mistake on our part. I guess it doesn't have to have a list. Thank you for pointing that out. He was saying that we define corpus list here, but we don't actually use it. So maybe it might be later on, potentially, that we use it.
You are correct. It's later.
Okay.
Sorry.
So,
That's my fault.
yeah, sorry about that. Thank you for pointing that out, though. So we define TF-IDF, a vectorizer, initialize it, and then we do that fit transform that we've learned about before to actually apply it to the data. And you might have noticed that my runtime just got disconnected. Don't know if that happened for anyone else. Not a big deal. You should just be able to click this a few times and it will come back. Sometimes it just kind of clears out the resources. It'll keep all of our variables and stuff in there. So we just have to wait for that to come back here, but that should come quickly. Maybe. Always when you need it, right? Doesn't show up. Sure, yeah.
If we look 2 grams, then it doesn't know any knowledge about English phrases, right? Because not English phrases are over 2 words.
Mm-hmm.
But if it does 2 grams, we will cut. It doesn't know the correct way to cut the sentence phrases.
Yeah, you want to dive into that, Ray?
Yeah, so this is kind of getting into the tokenization, like how you choose to break it up. There's a pre-built one. You can actually also define your own tokenizer if you want to have it choose how to break things up. So if I were to talk about the default one that's in here, it's basically stripping, it lowercases everything. If I recall, I think it also strips out some punctuation. And then we told it to strip out stop words. You can also tell it not to do that if you like. And then it's just looking at whatever 2 words are next to each other and kind of going across them. So I always do this thing of like the cat in the hat. So I try to not mess it up. The cat in the hat is like your chunks. So it's the cat is a bigram, cat in is a bigram, in the. So that's the way that it works across it, if that makes sense. And then it counts up all of those bigrams, and whichever ones have the highest count, that's what you get in your chart. Does it make sense? Okay, yes. Okay.
Okay.
Yeah.
Good call on that. It will give slightly different results if you don't have the exact same thing that we do. So just with that, if that's just meaning it's using the defaults, which I think it uses stop words, and I think those might actually be defaults.
I think they are technically the
so
defaults.
I think you're okay.
But yeah, so if you wanted to change it to not do stop words, I think that would be a problem. But it defaults to n-gram of one a unigram. I know that for sure. And then yeah, I think it does English stop words by default. So
yeah, thanks. Sorry about that, guys.
yeah. Keeping track of differences between 2 notebooks is not fun. But yeah.
Awesome. Okay, any other questions on TF-IDF? Cool. Okay, so what we're going to do now is take TF-IDF, what we learned there, and go through a text similarity example. So Ray talked about like semantic and lexical similarity. What we're going to start with here is a lexical similarity technique. So what we're going to do here in this example is find in our data set what are the most 2 similar reviews to each other based on the text. And since this is a lexical method, this means we're literally having to look at the words themselves. Like, are they literally the same words between the 2 documents that we're looking at rather than the meanings of them? And so to do that, there's a bunch of different ways you can do text similarity, like tons and tons of different ways. Could probably be its own course. We actually did teach an NLP course last year, if anyone was in that, but we went through a lot more than this. But what we're going to use today is cosine similarity. And I'm not going to go through like the math behind it. I don't think we really have to know how that works to be able to do this example. But the general gist of it is we're going to take the cosine angle between 2 text vectors based on our TF-IDF counts that we got. So to do that, you guys can go ahead and run that cell if you like, if you haven't already. That's going to start printing out a bunch of numbers here that we'll explain here in a sec. So scikit-learn has a lot of different ways that you can do text similarity. We're going to import cosine similarity there, and we're going to run that on our TF-IDF vector that we created earlier. So to do that, we're just going to call that cosine similarity function, pass in our TF-IDF that we created. And then we're going to save that off as this cosine similarity matrix. And what I'm doing here is just printing out the first 10 rows in our matrix. So what this is doing is taking every single data point in our data set, and we're working on the titles. So we're working on the title of our article. So it's going to compare every single title of each article that's in our data set to each other. And that's what this matrix that we're printing out is showing. You'll notice here across this diagonal, maybe it's a little bit hard to see, I suppose, but you should be able to see on your screen there starts to be this diagonal of all ones here. Before I explain that, let me back up and say cosine similarity, it goes between 0 and 1. 1 being two things are identical to each other, and 0 meaning they are not at all similar. So this diagonal of ones here, what that's showing us is that it's actually the review or the title of our article compared with itself. So if you're comparing something to itself, it's going to be exactly identical, so we get that value of 1. And we get that across the diagonal. But otherwise here, what we get are all the individual cosine similarity scores between each of our other data points. So that's what our matrix is showing here. Yeah, question?
Is it unusual that the fourth row has all zeros except for the diagonal?
Yeah, it's not similar to anything else. Yeah. And remember, this is lexical similarity. So we're talking about they share words in common.
So no common words.
So there's nothing else has similar words in it, basically. Yeah.
Yeah, at least so far in this printout. It's definitely possible maybe somewhere across here.
Yeah.
No, yeah.
Yeah. Right.
Could point to a data quality issue potentially in our data set, maybe something that we need to investigate and clean up. It's a good call out there. So we got this matrix, but what the heck does that matter to us? Like, why would we even use this? Well, what we can do there is actually take our matrix and with a little bit of matrix math, we can get the two most similar article titles to each other. So that's what we're going to do here. You can go ahead and run this cell. I'm going to explain here what we're doing. So to do this matrix manipulation that we're going to be doing, nothing too crazy, like you don't need linear algebra or anything to do this, so don't stress if you are trying to rack your brain on matrix manipulation. We're going to use a library called NumPy, which is also very popular. You guys probably use this library, I don't need to explain it. But what we're going to do is find where is the highest value in our data set. So we'd be looking for a 1, presumably, but you'll notice we've got this whole diagonal of 1s that I just explained is a review, or I keep saying review. It's the article title compared with itself. So we don't want that to show up as our most similar item because it's the thing compared with itself. So what we're going to do is use NumPy fill diagonal and then pass in our matrix and tell it what we want to fill it with. So I'm going to fill that with zeros so that it doesn't pick up on those when we do our max here in a second. So we fill the diagonal, and then after that what we're doing is using this argwhere function from NumPy, and that just allows us to search through the matrix and to say what we want to get out from it. So in this case, I'm searching my matrix and saying where's the max value. So that gives me the indices of where that is, and then down here I am printing out the the title of the review that were most similar to each other. So we print the maximum cosine similarity. We did have a 1 in this case, so they're perfectly similar. And then we print out that value as well for the title. So we get Xiaomi Mi 3 review, and then the same thing but with a 9. So Ray, remind me, what did we say on these numbers here? So they're not technically identical. They're two different numbers.
Yeah, but essentially there's a couple things that could be happening here. We haven't explored it deeply. Remind me, this one we're running off of TF-IDF.
Yep.
So one of the things that can happen is that your numbers are getting squashed down with TF-IDF. This data set is a bunch of product reviews, and if you think about it, like a lot of companies use numbers to name the version of iPhone 11, iPhone whatever, so numbers kind of get squashed out a bit. And so those vectors end up being really, really close to each other. It's probably not technically perfectly one, but it's close enough, and it just kind of rounds up to it, if that makes sense.
Thanks. That wraps us up on lexical similarity. We're going to go to semantic similarity, but I'll pause for questions before that. Yes? Sorry, I did not catch that all the way.
Yeah.
Right, so the question was what we're analyzing it on, and yes, so what we did our TF-IDF on earlier was just the title of the article, so not the actual content of them themselves. I think in our next example we are still using title, but you could, definitely, if you wanted to play around, go back in there and just switch out that column name that you're talking about rather than the title, use the article text itself. Good question. Okay. We're going to go on to sentence transformers. So like Ray mentioned, there's a lot of, or sentence embeddings rather. Transformers, embeddings, kind of same thing. So there's a lot of different ways you can do this, like at the word level, at the sentence level, at the document level, probably even larger than that if you like. And there's popular ways to do that, or popular methods for it. Two popular ones are word2vec and BERT. So just letting you guys know about those, and I've got links to those in case you want to check those out on your own time. But what we're going to do, if you want to go ahead and run that cell there, is use a library called sentence transformers that makes this pretty easy for us. So we're going to install that into our environment, and while that is running, I'm going to talk through this next section here. So what we're doing with this library is we have to tell it what model we want to use. Don't worry about that too much. This is just the name of the model for the sentence transformers library, something called all mini LM and some version number there. So that's the model we're going to be using to create our sentence embeddings. And what we're going to do is just pass in what we want it to encode or transform in our data set. So this doesn't print out a billion different things and it runs pretty quickly. We're going to limit this to only the first 5 titles in our data set, or I guess maybe 6 if we're indexing at 0.
Is this a word2vec or a Berg transform? Or is it?
That's a great question. It's actually BERT. So the sentence transformer side, if you go look at their documentation, they mainly work off of BERT-based models. Yeah.
Good question. So we will define what we're going to do. We're going to do that first 5 titles in our data set, and then here what we do to actually create the embedding is we call this model, and then we do .encode on it. So if you guys want to go ahead and run that, it should print out a bunch of stuff. We're just going to show you what an embedding looks like. Probably doesn't really make sense to most of us. We can't really interpret it, but this is just to show what all it's doing to create it basically into numbers for a computer to understand from the text. So I can scroll back up here. What we do is just print out what title are we looking at. It gives you the dimensions or the size, and then here is the actual embedding. So can't really interpret that at all. So not really useful for us, but just wanted to show what an embedding ends up looking like. And so same thing here, what we can do actually is get 2 titles and see which ones are most similar based on this semantic way. So remember, semantic is they don't literally have to share the same words, but rather the same meaning behind the words. So here what we're going to do is just take 2 indices. Since we only had 6 in our data set, I'm just defining the 2 that I want to compare to each other. We're going to print those out. We're going to encode them individually each. And then we're going to run a cosine similarity against those. So that technique we learned about earlier. But rather, instead of passing in TF-IDF, this time we're going to pass in those sentence embeddings. Don't worry too much about this reshaping stuff. To use cosine similarity, we have to get it in a certain format. So that's what we're doing there. So if you want to run that, what that will do is print out the 2 title of our articles that we're comparing against each other. So we've got one that's a B-Link T4 Windows Thin Client review, and then one that's a HP Star Wars Special Edition Notebook review. So you'll see that they, I guess, only have that review word in common, but everything else seems to be pretty different. But we get this cosine similarity score of 0.21 if you round up. So not a super high score, but what this is telling us is that even though they don't really share a ton of the same words, they mean the same thing. So a thin client and a special edition notebook are probably both laptops, so this is recognizing that those are both talking about the same thing and being able to score those as similar to each other. Any questions there before we pause for a break? Yes?
The cosine similarity, that's of that 384 dimensional vector?
Yep. Yep. Question up here?
The model has to be trained using cosine similarity as well.
So question was, does the model have to be trained using cosine similarity?
Not to my knowledge. It doesn't have to have cosine similarity in its training. So the word embeddings is one piece of technology that allows you to represent some text semantically, and then you can take the cosine similarity between any two vectors and see how similar the vectors are to each other, which maps back to how similar the original text was, if that makes sense. But they don't have to be trained with any cosine similarity.
I'm just imagining that when those models were trained, their progress was to quote words that are semantically similar, closer to each other.
Yeah.
So they have to define a distance function.
I understand, yes. So that's true. So there is a form of what you might, well, not all embeddings actually function quite that way, actually. But I get what you're saying by defining a distance function. There is a distance function. I was trying to say, it doesn't have to be the exact same distance function is, I guess, what I'm trying to express. Because there's a lot of models that you can plug the embeddings into that function off of different distance functions, and yet the vectors are still close to each other, relatively speaking, in space semantically, even though the way you're calculating the distance may be slightly different, if that makes sense. So it's not required that it uses cosine similarity. Yeah.
Yeah.
Mm-hmm.
So you could do as you did above and compute the cosine similarity over the whole n by n of the titles.
Yes.
Find the largest, you could find the most of the titles.
Absolutely.
Thinking example, yeah.
The
Yep.
problem is that this Google Colab is free and it doesn't have enough RAM to do that. But yes,
Yeah.
absolutely could.
Yep. Yes.
One thing we were asking about is just if you're limiting the corpus, you're using that corpus list. which
That's
is
right.
Like the 500
Yep.
check radar sample. But then are you also limiting the encodings, or is that going to be the same number?
No, great question. So the library, we're not limiting the encodings, but we limited the list again because we're running on a free Colab that doesn't have enough RAM. I actually ran it with the whole thing originally, and it died because it did not have enough RAM, and then I backed it off so that it could run successfully here.
We were just looking at the products and they're nothing alike, you know?
Well, they're both actually referring to compute. So semantically, they actually have some similarity to each other. But the similarity score you'll note is 0.2. A perfect score is 1, so it's not a high score by any means. So, but they are both in reference to compute. So there's a little bit of relationship, which is what it's picking out. If we ran a different type of vectorization technique, it would be 0 probably all day, every day, because there's, like, words-wise, they're not similar, other than review. Yeah.
Yep.
Yes. An embedding is different versus what? So, like word counts and TF-IDF, how are they different from each other? Is what you're asking, yes? How it's different from an embedding? Yeah, so I'll try to express it as simply as I can. In the case of word counts and TF-IDF, that is basically a number. The vector that's being produced is just a direct calculation of which words appear in the document. Whereas the word embedding, what it attempts to do is to construct a vector in space so that if two words are similar to each other, they're close to each other. So they don't have to be the exact same word for you to actually see that they're similar to each other. So a classic example is with analogies where they say like king and queen. Those would be the vectors for king and queen in a word embedding would be close to each other because they're similar. They're not the same thing, but they're close to each other in space. And if you ran a cosine similarity on king and queen, you would see that the similarity score is pretty high. Whereas if you did TF-IDF or word vector, the similarity is 0 because they aren't the same word. So that's the difference, if that makes sense. Cool.
Awesome. Great questions, everyone. So I think that leads us up to our exercises. But before we do that, we're going to actually take a 15-minute bio break for everyone, because it's probably very well needed at this point. So go ahead and get on for your break. If you want to get a head start, you can read through the exercises, but otherwise I'll come back and talk about those. I think we are ready to come back here. Hope everyone enjoyed their break. I'll give you guys just a second to wrap up your last combo. Cool. Okay, so we are back. What we're going to actually dive into now is some exercises for you guys to have some fun with. So if you haven't already gotten a head start on these during the break, no worries. We're going to give you guys about 15 minutes to go through 2 exercises here. And so what we're going to do in this first one is we're going to do, or it's all about really just stuff that we've done already, just kind of further expanding on it a bit. So what we're going to do here, this is talking about similarity between product reviews, or between a certain product category. So in our data set earlier, we were looking at one point we were looking at the entire data set, and then another point we scaled it down to just like 5 examples. In this example, what we want to do is filter down the data set to a specific product category. Doesn't matter which one you choose, and choose whatever one you like. You'll do that, and then you'll use the techniques we learned earlier to figure out which 2 reviews within that category are most similar to each other. So should be able to use some of the code that we learned earlier, and I don't think I specified like how to like create the data behind the scenes for it, so feel free to use your creativity there. So that's activity 1. And then activity 2 is getting to a little bit of machine learning and using a technique called nearest neighbors. If you don't know what that is, it's no big deal at all. We've actually, I think, got most of the code in there for you guys to use. But one of the things we have to do a lot is find similar documents to the ones that we're currently looking at. And we talked about how that can be used for like records matching, duplicate records, plagiarism, all that stuff. But one way to do that is through like a nearest neighbors unsupervised machine learning model. So what we'll have you guys do is use that machine learning model to find the most similar articles. And we've got some helper text in there. Again, use your neighbors, pair programming, and then Ray and I will be walking around as well if you've got questions in the meantime. So I'm going to set a timer for 15 minutes, and you guys can get going on that. All right, guys, we've had our 15 minutes. That actually went by really fast. I don't know if it did for everyone else. A quick like thumbs up, thumbs down on how this one went, or maybe Okay, yeah, this one was a little bit more challenging than the last one for sure. So I think, yeah, let's just start going through the code. This was how we chose to solve it. The beauty of coding is that, you don't have to have the exact same answer as us. This is just one way to do it. But first thing we had you guys do is pick your own category that you wanted to work on. So for us, we chose the cameras category. So using that syntax here for filtering down a data frame so that we're only working with the cameras category. And I'm just calling that subset. So I'll run that. And then what we chose to do, so you guys could have chosen to do TF-IDF or another method. We chose to do sentence embeddings here because that would be the most complicated thing that anyone would be doing here. So this required a little bit of like reshaping to do that. So a little bit tricky there, but I'm gonna go ahead and run that and we'll see what that prints out for us. So we chose to do sentence embeddings, like I said. So what we did was calculate those using the code that we learned earlier, and we just have to have 2 for loops here to loop through all of our data to create that cosine similarity matrix, calculate that cosine similarity there, and then we are just creating our matrix basically with this append here. So when we do all that, it's gonna keep printing for quite a while, but we get that nice diagonal of 1s, so that's the review compared with itself, and then the rest of our scores are those cosine similarity scores for our sentence embeddings. Once that finishes, I think that, oh, it's getting close to run, maybe. So then the last part of that was a bonus, like if you had extra time to do that. So this was finding the 2 articles with the highest similarity. And so we did that similar to what we did earlier. Since we did these sentence embeddings, what we had to do was reshape our matrix so that we would be able to fill the diagonal on it. So that's what we're doing here, is just reshaping it based on how many titles that we had in our data set that we were working with. So that's what we did there, create that similarity matrix, and then fill the diagonal like we did earlier. So set that with 0s, get the max, and then print out those values. So for us, the 2 most similar that we found were, had a cosine similarity based on the sentence embeddings of like 0.77, and these were our 2 reviews. So looks like 2 like Panasonic cameras, I think. Is Panasonic a camera? I'm not sure, but sounds like 2 similar products to each other.
Can you scroll back up just to where you're doing that double loop part? I was just curious.
Yeah.
So you're just getting, on this model that you're calling on, what's that model code?
That was the one we created earlier, the BERT sentence transformer from that sentence transformer library.
Oh, okay, got it.
Yep. And I should mention, we're gonna send out this instructor's notebook afterwards. You guys have the answers to everything, so no stress if you're if we're going pretty fast. I know we're moving fast, and we're actually a little bit short on time too, unfortunately. So trying to keep moving through. So that was that first exercise. The next one was using nearest neighbors, and a lot of this code we already had in there for you guys. This was actually something we did at our work, so we decided to include it in here as well, just as a real life use case. So what we had was this first cell here. I think that was already given for you guys. This is running a k-nearest neighbors model from scikit-learn, and I think using TF-IDF, to transform our text for us. All of this like junk down here is just getting some extra information to return back the results appropriately so that we can interpret them. So don't stress too much about that. This was also, I think, given to you guys. So we had to reset the index on our data frame, so that's what we're doing there. Then we go into where you guys came in. So this was creating a feature using one of the techniques that we learned is to be the input for the model. So for this one, we chose to do TF-IDF. So we created our list of our titles, called that our corpus, set up TF-IDF like we learned before, did our fit transform, and then, passed that into our model in this next row here, or this next cell, sorry, rather. Did anyone try out sentence embeddings? Just curious. That was probably a little bit challenging, so TF-IDF was probably the way to go on that. Yeah. Oh, gotcha.
So it doesn't go into the data frame.
Right.
It's a new feature.
Right. Yeah. So question was about putting TF-IDF like back in the data frame. I can see why you might think that, because I think that's what we did with like one-hot encodings and things. But yeah, for TF-IDF, we don't add it onto the data frame. We just have that. We create that on its own, and that's its whole like set of counts and things that it's done, and just pass that into the model itself.
Yeah, for this example, there's another technique, and I know we're on time as well, but in scikit-learn, there's like a column transformer, column transformer. And so you can actually define the vectorizer that you want to use or whatever feature creation and apply it across a data frame using what's called column transformer in scikit-learn. So I know that wasn't represented here, but as far as adding things onto a data frame and such, column transformer I think is the way to go for that.
Yeah. And then these next couple of cells I believe you guys had, so really it was just creating the feature there. That's the input for the model. So we'll go ahead and run that. And then this was showing our results, I believe, in these last few. So this was giving you those results. And I'm not going to explain this too much. I'm sorry. We're a little bit short on time. So we're going to pass it back to Ray, actually, and he's going to go through exploring continuous data. So all of this, we've been working with discrete data up until this point, but there's a whole other kind of data set that we haven't even touched on yet. So we will go back to Ray for that. And sorry, let me get the slides back up to the right spot. Oh, wait. Yes, we're on that. Okay, good.
Thank you. Okay, so yes, exploring continuous data, our other big data type that we're going to mess around with today. So continuous data examples, things that can range from basically negative infinity in theory to positive infinity, like the whole real number line. Obviously, probably don't have negative height, but height, age, weight, temperature, distance, these are all forms of, generally speaking, continuous data sets. We'll keep it moving. Ways of exploring continuous data sets. Yes, you are seeing some closing stock prices listed here. That's the data set we're going to be playing around with. So it's technically time series based data, but line charts are a classic way of exploring it. Box plots are another fun one. That was a blast from the past for me, as far as doing like the old box and whisker plots. Yeah, whiskers. They don't, I guess, use that terminology anymore. But we're going to show that off. And then heat maps are another way to go about it. I've always been fond of these. I've used them in a number of situations because, you know, your standard X, Y, you have 2 dimensions, but adding in color gives you like this third way of like visualizing a third dimension of data. So I'm a big fan of heat maps. And then scatter plots. Can't get away from those. I'm going to assume most everyone's seen a scatter plot before. You got your X and your Y, and you're able to do a comparison across 2 pieces of data. In this case, 2 continuous pieces of data, hypothetically. Okay. That's going to be as fast as I can breeze through that so we can get to some actual coding.
Cool, thanks, Ray. All right, back to the Colabs. We're going to talk about how we do this in Python. So, like Ray mentioned in the slides, we're going to be using a different data set for this section. We're actually going to be using some stock data. Hopefully something that a lot of us are familiar with, but if you're not, don't worry about it. It's not a big deal. So first off, we can run that first cell there. We're going to use a library called yfinance. If you haven't used that before, really handy library to pull down stock data. So you don't have to like go out and download a CSV and all that stuff. A really nice library there. And we'll also be using pandas here to explore as we have been before. So we can run that next cell. What we're doing there is using the yfinance library to download specific stock tickers. In this case, we're looking at indexes or index funds. We're looking at SPY, QQQ, and VIX. And then we also pass in a start and end date range. If you want to, you can pass in your own tickers if you like, if you have a favorite stock, and also do a separate date range if you want to. But if you want to match up to what I'm doing here, then just leave that as is. So we are just going to analyze data for those 3 indices from all of 2022. Run that next cell, and let's talk about the format of this data. This is printing out just the first 5 rows of our data set. You'll notice here that we've got like some hierarchy going on in our data. So you'll see like we have an adjusted close column. So these are all about like the price of the stock at certain points. So this is what it closed at on that day, the high price for the day, the low price. We get the open and the volume as well. But actually before this workshop, I had never used this kind of a data frame before, but it's really nice, and I'm glad I learned about it. It's called multi-index, or multi-label is another way to call it. But what it allows you to do is just have a hierarchy in your data set. So what's nice, we'll see later, is that we can just reference like this top level column, and it will give us the 3 columns underneath of it. So that makes it really nice for plotting. We'll see that in a second. But just wanted to highlight the format of our data here, a little bit different. So you'll also notice that each row here is an individual day, and then we've got all that information about the price as well as the volume of those stocks on those days. So we're going to use our friend from the past, our wide data profiler library, to be able to explore this data. So if you want to go ahead and run those 2 cells there, what that's going to do is, first of all, unfortunately that library cannot handle multi-index data frames, so we just have to, if we want to explore it, to download 1 stock at a time. So that's what I'm doing here, is just only downloading SPY for that same year, and then saving that off as its own data frame so that we can run the profile report against it. So that is the one downside of that sort of data frame style, is that not a ton of libraries will work with it, unfortunately. But we can work around it. It's not too big of a deal. So like before, you guys should be familiar with this kind of report now. We're getting the same thing, but for time series data. And I mentioned earlier that there is a parameter you can set on the profile report so that it makes line charts for you out of the box, which is nice. So we're using this extra parameter, TS mode equals true, to tell it that it's a time series, and then I'm just saying that we want to sort by the date column so that our line chart makes sense, like over time. I'm not going to go through this because that is going to be, again, an exercise for you guys to go through. So we will skip a little bit through that. And then now we're going to talk through how to make all those charts that Ray was talking about. So first up, we're going to go through line charts. What we're going to do is just plot each ticker's close price. So you can go ahead and run that cell there if you haven't already, and that gets us this chart from the slides that we saw earlier. So we get over time, what was the close price of each of those tickers, and they're color coded. And I'm just setting those colors here. You can pass in your own colors if you like. That's just a thing that's built into this plotting. You could also do this with a library like Matplotlib or Seaborn, but lucky for us, Pandas actually they've done some work to like wrap Matplotlib into the library so that you can just call this dot plot instead of having to write a whole bunch of code. So that gives us a line chart. What we'll notice here is actually that this VIX index appears to be on a different scale than SPY and QQQ, so it can be a little difficult to see like what is the actual trend going on here. So one thing we might want to do is split that off into its own chart, and that's what we're going to do next. So to do that, I'm going to run that next cell. And how you like access this in a multi-index data frame is by using these parentheses on the inside. And so you first call what high-level column do you want to look at. In our case, it's the close column, and then what specific column underneath that. So I'm just saying only give me VIX. And what that does for us is give us a chart like that. So we can better see what trend is going on. You could also like manipulate this scaling if you want. I'm just leaving it at the default, which is maybe not a best practice for data viz, but for ease of the workshop, that's what we're going to do. And we can also plot those other two together if we wanted to. And to do that, what we can do is use that same like parentheses notation, but then just put a comma in between them. So we're saying give us the close for SPY, give us the close for QQQ, and plot those together. So if you can run that next cell, and then you get that. So you can see a little bit better the trend that's happening when they're on their own versus when we've got that other one that's unscaled. Any questions on line charts? Pretty straightforward. We probably all have done line charts before. So let's get into stuff maybe we haven't done before, or and maybe like mine and Ray's case, haven't done since like middle school or elementary school. So we're gonna go with box plots, a really great way to visualize distribution of your data and also see outliers. To do this, we're gonna use a library called Seaborn, which is another really powerful plotting library. But to get it ready for Seaborn, we have to format our data a little bit. So we got to do a little bit of data engineering here. So I'm in these cells, or in this cell right here, I am formatting the data the way that I need it to. I'm going to go ahead and run this so that we can see the format that I want it in, and I can talk through that. So what we're doing here is getting rid of basically that like hierarchical structure that I was talking about is really nice. That was nice for the line plots, but not for the box plots that we're gonna want to do. So we are using this stack, level 0, to get rid of that, and then also format it this way. So instead of also having a column for each ticker, we now have one column called ticker and a row for each one. So instead of being a wide data frame, we're taking it to a tall. So then we get our close value. One thing we're going to want to do in our box plot is plot everything by month, but that means what we have to do is we have to get from the date what is the month. And this gets a little bit actually into our feature engineering section that we're going to talk about later, so a little bit of a precursor here. But to do that, what I'm doing is using this string f time, string formatter time function, and that allows you to take any date and then format it as a string based on the formatter that you pass into it. I am doing the 3-letter abbreviation for US months, or US version of those, and the way we get that is with this %b. So that's what I'm doing there, and now our data has been pivoted correctly so that we can do our box plot on it. So let's actually create the box plot. So run that next cell, and we get some nice box plots, but it's a little bit hard to see what's going on. So this is a way we can get box plots for each month, for each ticker, for the close price of those. So it gives us a good view of the distribution of those, but a little bit hard again to see like what's going on with VIX down here. So there are some other ways we can do this and split it out. One way we can do that is the next cell, which is using something called cat plot in Seaborn to actually put them each on their own plot. That helps us a little bit here, but still hard to see what's going on with VIX. So I should have selected VIX down here, but I'm just showing you that you can just plot one at a time. So if you wanted to see VIX on its own, just replace SPY with caret VIX. And then what that does is give you a nice chart that you can actually see what's going on and identify some outliers as well. So really handy being able to do those charts. Any questions on box plots? Yeah?
Colors here mean anything?
No, they don't, which is probably another like bad data viz practice of me to do. So. Very true, yeah. I should have done that. Sorry, I did not. Good question. Okay. And next up, we're going to do heat maps. Ray was talking about these are really nice that you can see like 3 dimensions of data in one chart. So here, color will actually matter. So what we're going to do is we need our data formatted also a little bit differently to work with a heat map. But first, what we want to do is when we're making our heat map, we're going to actually do what was in the slides, which is for every month on the x-axis, on the y-axis, we're going to have our days, and then for color, it's going to be that close price. So we need to extract the day out of our date that we have. And to do that, there's a nice built-in function just called day that we can call on a date and get that pulled out. So if we run that cell there, what we'll see is we added on to our data frame what is the day, and so the heat map needs that information. It, unfortunately, not to my knowledge, can't like parse out from this date, unfortunately, so we just have to do a little bit of prep to get that ready. So then what we're gonna do is just filter down to one ticker at a time. So we're gonna filter to SPY, and you guys can go ahead and run that cell too if you haven't already. We have to pivot the data again because it just needs it in a little bit of a different format, so that's what we're doing there. And then Pandas annoyingly orders columns alphabetically, but if we're dealing with like time series data, alphabetical order doesn't make sense. So I am just I'm telling it the order that I want them in, which is, you know, what we would normally expect for a time series. So doing that and then ordering the months so that works out. And when we run that last cell there, this actually creates the heat map for us. And I might zoom out a little bit here so we can see it all on one screen. So we'll see on our x-axis we have the months, y-axis we have the day of the month, and then that color chart is showing us the close price. So higher close prices being that darker color, lower prices being the lighter color. So this is a nice way to get us to see 3 dimensions of data at once. Can be a little bit tricky here, I guess, interpreting this, because you might be wondering, why the heck do we have all these blank spaces in it, or white's not in our color chart? Well, that actually happens because the data that we're dealing with doesn't have weekends in it, because stock market isn't open on the weekends, so just doesn't have those, so that's showing we have no data there. But you know, some months the weekends are on different days of the month, so that's why we still show all the days on that y-axis, but just not showing all on the chart. Any questions on heat map before I move on? Okay. And last one in this section is scatter plots, which, like Ray said, probably a lot of us have seen before. You can go ahead and run that cell there. What we're going to do here is plot on the x-axis, we're going to plot the close price, and then on the y-axis, we're going to plot the volume. And so what we're looking for here, scatter plots are good for seeing if two variables are correlated with each other, and that's what we're trying to see here. Basically, is the close price correlated with the volume, or vice versa. How we interpret a scatter plot, I have it written out here if you haven't seen one before. Positive correlation would be if our data was moving from this bottom left corner all the way to the right, top right, to kind of in a line like that way. That'd be a positive. So both data points, as one increases, the other increases. Otherwise, you've got negative correlation from the top left down to the bottom right. Or in this case, it looks like we've got no correlation, appearing at random, basically. Okay, so I think we're ready for exercises. We're going to give you guys 10 minutes for this section. One of it's going to be just exploring the data using the profile report that we learned about earlier, so hopefully that should feel pretty familiar. And then the other section will be visualizing the stock data. Using the techniques that we described above, we only, remember, looked at the close price basically, but there's 4 or 5 other columns of data you can explore. So that's one thing to do there. And then also, if you are a fan of some kind of chart that we didn't talk about or know of something, feel free to use that for bonus points. So with that, I'm going to put 10 minutes on the clock, and we'll let you guys work on that. All right, there you go. All righty, I think we're wrapped up on this section here. Again, quick thumbs up, thumbs down, thumbs sideways, and how we did? Okay, seeing lots of thumbs up, good deal. Was hoping for that because a lot of it is what we did in the previous section, so nothing too new here. Okay, so I'm gonna explain these here, and then I realize you guys are due for another break, so right after I get done explaining this, we'll do another 15-minute break, and then come back. Okay, so for exploring, what we did here was just use the code that we had earlier from the Y-Finance library to download the specific tickers that we're interested in. In this case, I'm downloading QQQ here, and then doing that for 2022. Same like we did earlier, so mainly just a copy-paste, but switching out to the ticker there. Then we're using our code from above to create that profile report like we did, so we'll do that. And then that creates that, and you guys had plenty of time to explore, see what that's all about. So that's old news by now, so I won't go into that. And then same thing really here for this section. Second section was just switching out that ticker for VIX and then doing that same exploration. So we'll run all those. Okay. Then the next section was all about visualizing the stock data. So using some techniques that we talked about, or for bonus points, go through one that we did not discuss. So anyone do one that we didn't talk about? Oh, okay. Very cool. Awesome. So again, beauty of this section is your code should not really even match mine. This was just what we chose to do for this example. So we decided to do a heat map on the QQQ close price. So mostly just copying the code from earlier, but swapping out that ticker for QQQ. So doing that and seeing what that looked like. And then our second example here was looking at the volume column for QQQ. So most of our examples before, we looked at the close price column. So this is just looking at a different column. So mainly copying that code and then swapping out to whichever column you're interested, as well as this was on QQQ rather than SPY that we did in the examples earlier. So I won't go through that too much, but we get that nice plot here, which Same sort of setup as the other one, but you can tell values are a lot different. So nice to explore that too. And unless anyone has questions, I'll pause for a sec. Questions on either of those? Hopefully pretty straightforward. Okay, so you guys are due for a break. We're going to give you 15 minutes to go run around, stretch your legs, get some more water, go to the bathroom, all that fun stuff. Oops.
Alrighty, welcome back. I appreciate you coming back from your break. This will be the last fill or last section you'll have of me, and then we'll pass it back to Leah to walk you through the actual code and get you going on the final exercises. So, we've talked a little bit about exploring features for continuous data, and now we're going to talk about actually exploring the continuous data, and now creating features for said continuous data. A lot of it might be pretty darn familiar, to be frank. Continuous data is something that we do work with. Again, we primarily work with text data, but this is also a good thing to have in the tool belt. Most of our continuous data is coming in over time anyways. So let's dive in. So one of the first techniques is normalization. There's a number of different ways to normalize a data set. Min-max normalization is one of the ones that we tend to lean into. Here we have some X value that we're wanting to scale to normalize. We can take the maximum value that exists for this in, let's say, a field of data, and I'll show an example in a sec. Subtract it from the minimum value, and then for each individual value in the data set, we can subtract the minimum from it in this little fraction, and that'll scale it. So a nice example will help if you haven't seen this before. So here we start off with, for example, views on a set of 10 hypothetical videos. And we'll notice that the 8th video has the largest number of views, and the 10th video has the smallest. So those are like the two core ones to latch into immediately. And so from our chart that we talked about earlier, the denominator will be the maximum value minus the minimum value. And then in the numerator, we have the specific value for that row subtracted from the minimum value, which is 32. Just as a sanity check, when we look across all of this, we'll see that yes, our maximum value has been normalized to 1, since we get maximum minus minimum divided by maximum minus minimum. So two identical values over each other, that gives us 1, and then the 32 minus 32 makes this thing 0 at the end of the day. And then everything else is pretty much spread out, again, normalized across the span of those values. So that's one technique, normalizing the data set. Another fun one is log transformations. Leah will touch on this in a bit about the type of data that you'll want to have when you actually do this one. But there are some specific time periods, and stock market data actually is one of them, where you'll actually want to do a log transformation on your data set, in this case, your X value. Classically speaking, if you go back to your old algebra school days, your base of your log would be probably either 2, 10, or e, the natural number, and ln is the natural log there for that situation. Yeah, there's a little visual. If I have a data set X, what applying that natural log would look like at least. Okay, this is fun. Yeah, we have this in here too. So table example, we're looking at the same views from before. So nothing's really changed, we're just applying the natural log to it. And then we can see, unlike with the normalization from before, that was from 0 to 1, this time it's 3.5 all the way up to a whopping 13.8. But you know, that natural log curve should make sense as to why it's like squashing things in a non-linear fashion, basically. Even 500,000, which is roughly halfway, is at 13.1, as opposed to being on the previous one at approximately 0.5. So normalizing the way we would expect it to for natural log. Another technique, ratios. This one I have used a crazy amount, as goofy as that sounds. I think at the very, very beginning, hours ago it feels like, I talked about like just even something as simple as quality controlling sensors that exist. One of the things that we would do often is we'd put two sensors out in the field at the same time and then just take a ratio against the two. And if the ratio went way off whack, we knew one of the sensors was going bad. So
you would have like two in the same area.
yes,
Start diverging.
if they start diverging from each other, a ratio would point that out and we know one of our sensors has gone bad, we need to replace it in the field. Exactly. Yep. So ratio, I feel bad going too crazy into this. It's a division. So you got impressions, you got clicks. Divide one, clicks divided by impressions. We get our CTR, voila. So again, the previous ones we talked about, it's a transformation on one piece of data, one field, and the ratio gives you a transformation, giving you a feature for with a relationship between two fields. So a bit of comparison there. All right, some of our fun ones. Rolling windows. Let's imagine that each one of these is a month, even though we're stopping at 10. And we want to actually take a rolling calculation. So we would, for example, take 3 months worth of data and we'd perform some form of calculation on it. Let's say an average or a min or a max. It literally can be any kind of calculation you want. But we've defined a window. In this case, the window is a length of 3, and we roll it across with each one, and we do that calculation across each window as we're sliding it across. So there's a rolling windows approach. It does something nice. It actually smooths out your data set for you and can be really nice for actually capturing what the general trend is and kind of denoising some of the choppiness that's in there. So very popular technique, and yeah, I'll leave it at that. There's some folks that like to play with that in the stock market data, but leave it there. Here's a table example to go through. The big thing to call out here, we are doing average, but because we're doing this rolling and we have chosen 3, whatever length of window you choose, you're gonna lose that amount of data off the top, essentially. Because we've chosen 3, we can't have an average for the first 2 items. We have to go down to the third one in order to produce an average of 3 numbers. So whatever n is, the length of your window, n minus 1 data points are kind of gonna get washed out. Okay? And so that's all this is doing, is taking an average of the top 3 months and storing it here under March 2020 at 2.5. The next 3 months, February, March, April, get stored here as 3.1, so on and so forth, as we're sliding that window across time. I'm moving, but shout at me if you have questions. Okay. Something somewhat kind of related, but not exactly the same, is lag. So especially if you're dealing with time series-based stuff, lag is really popular. But anytime you have a data point and you believe there's a relationship between that data point, and again, it's usually time or sequence-based, you think there's a relationship to the next data point, lag is something that you want to look at. I should also note for fun that you can think of human language as a sequence. It has to be ordered for it to make any sense. You can't just jumble it in any order. And so there's kind of a relationship that occurs there. Yes?
I think one example would be like promotions, right? You offer promotions to a store that may take a couple days to
Yes.
back, and you want to lag.
Absolutely. Yep. Yeah, absolutely. So all we're doing is taking that data set and just shifting it. And so now we can look across time and run kind of like this correlation for March on the previous timestamp, which was February. So that's lag for you. Okay, date time. This is one of my favorites because a date seems like not a lot going on there, but there's a lot of like interesting information that's embedded in a date, technically speaking. So you can have, yes, the month, the day of the month, the year, so on and so forth, but you can have things like, is it the weekend, yes or no, or is it a weekday? That can be a feature that actually gets used. In fact, that's actually a feature that gets used, I guess it would be, in the cash department at the Fed. So when they're looking at how much cash is flowing in versus not, they really care about whether it's a weekend or a weekday, and we can extract that from a date as a feature. Likewise, with holidays, you get spikes in behaviors in the holiday section. So there's all this information that's actually kind of technically wrapped up in just something as simple as a date that you can extract out and use to make a clear signal for whatever process you're looking at. So with that pretty much sums up date time and at least a quick overview of features. Like I said, this is kind of the end for me on this part before Leah dives you into all the coding piece. I did mention at the very beginning that we are a part of Data Science Rebalanced, helping to try to bridge that gap between academia and industry. The core way that we do that is by offering a data science workshop where we actually teach about our own sort of data science life cycle, from acquiring the customer story and understanding to collecting the data, challenging the data, and even creating a demonstration that will move your customers to implement your solution. So the way our workshop works is we do video lessons. You can pace them yourself so you don't feel rushed like you might right this moment. There's actually a weekly live coaching call with us to actually help out with triaging personal feedback, career advice, anything in that kind of space. We also provide assignments and general broad community discussion around data science topics in our product. I wanted to give a shout out that our next workshop is coming up May 7th. If you have any interest, everybody at PyCon, 20% off, coupon code PyCon 2023. So with that, I appreciate your time. We got a few seats left in the spot, so if you have any interest, I would say definitely hop on it before it goes away. All right.
Sweet.
All you, Leah.
Yeah. Thanks, Ray. Yeah, we'd love to have you guys in the workshop if that interests you at all. Hopefully you've enjoyed what you've had today. We've got a little bit more left. We're on the very home stretch, and so not too much more here to go. Okay, so we're going to dive in again. How do we do all this stuff in Python? We're going to start off with our min-max normalization, and with that, we're going to use scikit-learn, which we've used before throughout the workshop. It has a built-in function to our rescue, once again, called min-max scalar. To apply it to our data set, what we have to do is just initialize it like we've done several times before in the workshop, and then we apply the fit transform to the column we want to transform. And in this case, we're going to do that on the close price of our stocks. This whole mess here is me just assigning that back to the appropriate columns. I'm calling it close underscore MMS for min-max scaling. So that's what I'm doing there. So if we run that, what we can see is in the data set, our data has been scaled between 0 and 1, just like we would expect. So it looks like on the first day of the year for all of these, or two of them, I guess it was when it had its max value, and then one had its min value that day. So that's what that tells us. So not really great at interpreting numbers just on their own, so let's plot them. We're going to use some plotting that we learned earlier. We're going to plot first the unscaled version, which we've seen this chart before. If you run that cell, same thing we showed earlier. Those are just the raw close prices for each of those indices. And then we can compare that to our scaled values. So if you remember actually from last time when we looked at this, that VIX was on a different scale, so we ended up plotting that on its own. But one way to avoid that is just by scaling the data. So that's what we've done here using min-max scaling. And so we can see they're all on the same scale now between 0 and 1, and we can see that trend, what's going on there better. Questions on min-max scaling? Purpose? Yeah, so a lot of times for when you're trying to create inputs for a machine learning model, what you want to do is scale your data so that the model doesn't like handle outliers, or it handles outliers better. Ray, you got anything else you want to add on to that?
Well, maybe not. Oh, there we go. The only other thing that I'd note is that there are situations where you may want to compare different pieces, different columns of data that are on drastically different scales. And so you can actually normalize them and get a little bit closer, like how are they moving or behaving relative to each other in the chart visually, so that they're not so spread out if they're too much of a difference in scale between them. So that's another technique we've used for that.
Yeah.
Example was given that columns must be same length as key on that first box.
Sorry, say that one more time.
So that right there, I was getting
Yes.
columns need to be the same length as key.
Oh, shoot. Do I have an error in there?
From the DF docs. Okay, I'll look at DF docs.
Okay. Sorry. Probably another mistake on my part. Sorry about that.
I think I overwrote DF docs.
Oh, gotcha. Okay. Yep, no problem. Oh, yes.
So in this case, each stock is being scaled, being normalized to its own scale, not to the scale across all three, right? I mean, so you could argue this is confusing now.
Yeah, it's true.
Wild fluctuation in mix.
Yeah, no, you're right. If I were to, so for this example, we just like ran it across each one separately. But yes, if you're looking, depending on the situation, there's a number of times where you would want all of them to be scaled across the same sort of general range, I guess is what we're getting at, yeah. But this isn't, I guess it's more of an example of how to do it in code as opposed to exactly how you would do it for your use case.
Yeah, I was trying to think, how would you run the scalar to accomplish that?
Great question. Couple different ways to go about it, technically. If I were trying to force it. Well, one way that I could force that is to actually technically split this up as a fit and then a transform separately. So for these, we've just been running fit transform all in one, but they actually are provided as separate calls as well. And you could do a fit across all the data, and then it would transform to your lowest and highest across all of it. That's the way you could, that's off the top of my head, the quick way you could pull that off. Yeah, great question.
Good call out. All right, next section is on how to do a log transformation. So Ray alluded to this earlier, but there are times when you should not do a log transformation, and there are times when you can. One of the base assumptions of when you're doing a log transformation is your data needs to follow a log normal distribution. And if your data doesn't follow that, you shouldn't really be using a log transformation. So, lucky for us, we picked this data set especially because stock prices are assumed to be log normal. But if you're not sure if your data does follow a log normal distribution, one of the techniques you can do to figure that out is use what's called the Kolmogorov-Smirnov test. That allows you to compare one distribution to another, so test if your distribution is similar to the log normal distribution, and you can pair that with a hypothesis test, so like back when you learned in your basic stats class about hypothesis testing, to be able to interpret those results. So got links to those. I'm not going to go any further really than that, since our data we're assuming to be log normal, but that's what you would do if you weren't sure if your data set was log normal or not. So to do a log transformation, NumPy actually has this built into it, and we're doing a natural log transformation, and that's wrapped up in this NumPy log function. So we're passing in the column that we want to do, and same thing as before, I'm just setting the new column name that I want to call it as, which is close natural log. So if we run that, we should get those values kicked out to us there. Like we did earlier, let's go ahead and plot those so we can see how that compares to the original data. So here's our unscaled data, and then that next cell there prints us out the scaled data. Any questions on log transformations? Okay. Next up, ratios. So it should be a pretty intuitive concept. We're just dividing two data points against each other. In stock market data and like stock analysis specifically, this is a concept called relative strength, where people will take two stock tickers and divide them out by each other to see how they're comparing to each other, and then make purchasing decisions off of that, whether you want to like buy or sell based on how that is doing. More info on that in that link there if you want to check it out. But what we're doing here is just using that division operator between the columns. And so I'm taking the close price for SPY, dividing it by VIX, and then doing similarly SPY divided by QQQ, and then QQQ divided by VIX. So when we do that, we get our ratios between those two, and that gives us what's called our relative strength in the stock market world. So we can plot those like we've done several times now. So we get our ratios there. And then kind of hard to see what's going on with the SPY QQQ, so we can plot those out on their own. So first I'll plot the other two on their own, just so they're on their own scale. And then likewise, we can do that with that last one there too.
That ratio.
Yeah. Yep. Any questions on ratios? Okay, we'll keep rolling into rolling windows. So what we can do with rolling windows, there's a couple ways we can do this, and we'll talk about two here. So one is using the rolling function from pandas, and then there's another function called pandas called resample that we'll talk about here. So what we're going to do here is calculate a 3-day rolling average for our close prices for each of our individual stock tickers. And how we're doing that here is all the way to the right-hand side over here. We're calling the column we want to do that on, which is the close price. We're calling rolling. We're passing in this number here, and that is telling us like what window we want to be looking at. In this case, our data is daily data, so it ends up being a 3-day window that we're looking at. And then finally, at the end here, we chain on what calculation do we want to do. Like Ray mentioned in the slides, you can do any calculation you want. If you want to do median, standard deviation, something way more complex than that, we're just going to keep it at average. Yes?
Does the rolling need to be have a date time index to work?
The question was, does the rolling need to have a date time index to work? And I think so. But it might not. It might just be able to take like position in the data frame. I don't know the answer to that.
I've always used it with date-based
Yeah,
data,
same.
but,
Always
I
used it
guess
with dates.
Might not require it.
Yeah, I don't know. Good question. So we can run this cell and we will get those values. And just like we showed in the slides, we end up losing a couple of days because we just don't have 3 days to calculate that average. But that's all right. Not a big deal there. So another way we can do this is through the resample function in pandas. What this does is a little bit different. So you'll notice here in our last example, we still have a row for every date in our data frame. What we're going to see here when we run this resample is that we actually like change the structure or like the frequency of our data set that we're working with. So instead of having a row for every day and maybe like putting the average for every row and repeating it, what we're doing is just like aggregating it up so that we have the last day of the month, and that's what we're showing is the average for that month. And so we do that with resample. You can pass in whatever value you want here. I've linked to the list where it shows you all of those different possible options. We're just doing month for illustrating that and then doing the average again here. But you could do the standard deviation, the median, whatever you want there for your calculations. And last but not least in this section, let's go ahead and plot those values so we can see the trend line here. So not like an easy way to do this out of the box, so I had to do a little bit of matplotlib plotting code here. So setting up 3 subplots here, setting the size on them, setting the format of the axis that I want it to show as, and then finally over here we're adding in what do we want to plot. So the first plot is going to be the daily data, which that's how our data came to us, so we don't have to do any transformation to that. Next one, we're going to resample at the weekly level to do a weekly average. Then we're going to resample at the month level to do a monthly average. Lastly there, I'm just setting the title and making sure we can read the font, hopefully, at this size. And so that gives us this chart that was in the slides, actually, if you were paying close attention. So we get that daily data first, which is the data that the way our data came to us. Then we get weekly, so that trend gets a little bit more smoothed out. And then monthly, we can even see the trend more clearly there. Okay, and then I'm going to go through this last section here. Oh, wait, sorry, 2 more sections. One is lag. So lag is very similar to that resampling kind of concept, except instead of changing the format of our data, we're going to just shift it down by however many we want to. So in this case, Pandas actually has a function called shift. So that's what I'm using over here. And then you pass in what you want to shift by. So in this case, I am shifting by 1 day because I'm doing this on our original data set that we were working with, which was daily data. But you could do, if you wanted to take like the monthly resampling that we did and you want to shift by 1 month, so have a 1 month lag, you could do that. The possibilities are endless here. So this is just one example of how to do that. We'll run that cell and then run the next one after that, and that shows us our results. So we get the original close prices here, and then all we've done, you'll notice, is just shift it down by 1 day. So this allows us on the same row to see what was the close price on that day, so January 4th in this case, and then we also get the previous day, which was January 3rd in that case. So it's a really nice way, lots of times used for like time series modeling, especially like ARIMA models, if you're familiar with those. They have like a base assumption that the thing before it is correlated with what's coming next. So that's why we use lags to be able to tell the model about what happened in the past. Okay, and then actual last section here is on date times. So Ray mentioned there's a lot you can do with date times. We're gonna just barely scratch the surface on it. So much you can do here. But what we can do is pull out actually a lot of information. Where did my mouse go? There it is. Okay, so I've linked out here. This is a really helpful resource that I found. It uses the string format time function that we found earlier, but it's a nice cheat sheet for it because this documentation is surprisingly hard to find. At least it was for me, like in the actual library itself. So someone made a website for it. So it must have been a problem for a lot of other people. But it gives you just a cheat sheet of all those different formatter options that you can pass in. Sorry, and I know this is probably small. Let me zoom in. So you can get, a variety of stuff just out of the box, which is really nice. I will say it does not do like everything that's possible with dates, so that's where you kind of have to come in and do a little bit of feature engineering yourself. And I think that's a few exercises we have. This doesn't handle like holidays or anything, so there's some custom things you have to write to handle holidays, but this is really nice for just out of the box if you need to get a whole bunch of these different formats. Right. Yeah, question was about the libraries for holidays. Yeah, there are holidays. So you can do like US holidays and any holiday in the world, basically, and they've already got the dates of all those prepackaged for you.
We have separate holidays.
Oh, yeah. Ray was talking about there's some bank holidays, too, that like are additional in there. Yeah.
Yeah.
Okay, so we'll talk through this here real quick. So what we're doing here is taking our date, that date column that we worked with, to use the string formatter time function on it, we have to do a little bit of manipulation here to get it in this series format, and then I'm using an apply, but there's probably other ways to do it. I think you were showing us some as well, so. This is just the way I chose to do it, but I'm just passing in those different formatter options from that reference document that we looked at earlier to get, for example, the year out of it, the month number. I'll go ahead and run this so we can see the output of it. We get pulling from the date, we're getting that year as a column, the month number. We can get the long version of the text of the month. We can get the short version of the text of the month. So many different possibilities. So that wraps us up there. Since we were short on time, we won't have time to go through all of the exercise, but I think for the remaining amount of time, we'll give you the time to do the exercise if you choose to do that. Otherwise, you pretty much have heard all we had to say today, so if you choose not to stick around, totally understand, want to go get dinner or something, but really thank you guys for coming to our workshop. Hope you enjoyed, hope you got something out of it. And again, just a plug for our other workshop. If you enjoyed hearing from us today, we do similar stuff on our free time and get to have live coaching calls with us if that's any incentive. So thank you again, guys, for everything. Oh, yes. So sorry. Great question. So I will send out the instructor version of the notebook that has all the answers, including the last section that we didn't get to. And I'll send that out through there's like a message attendees option. Yep. So the one you got to set up the course, it'll be similar email there. Yeah, I can send that today. No problem. Yeah. And we'll be hanging around for questions too, as well, if you want to come up and chat individually. Yeah, great question. The question was about, we used a lot of libraries today. How did we find those libraries? How do we know what libraries to use? All that good stuff. So I'll take a crack at it, and then you can add on to Ray. I'd say for general, like in data science, there's pretty typical ones that you get used to. Like, it's kind of like a tech stack for data science, I would almost say. So like pandas, numpy, scikit-learn, those are like really popular ones that we probably use on a day-to-day basis. So just going through projects over time, we've learned that that's the tech stack, but that seems to be community-wide. That's what the tech stack is. Other way I would say is Google. I usually am Googling like every single day for my job, and then I'll find libraries that way on Stack Overflow, like someone using a certain technique. That's where I pick up on new stuff a lot of times, like the Y data profiling library was a new one that we picked up just from searching the internet. So that's one way for me. There's a lot of online resources as well, like Towards Data Science is a popular Medium publication that usually people are on like the cutting edge of new packages that come out, and they'll write up an article about like how they use them. So we like using that resource as well. Ray, you got anything you want to?
No, you pretty much nailed it for me. I was going to say, as a part of most data science projects, even if I've solved a problem before, the reality is a lot of times stuff is updated since the last time I worked on that type of problem. And so I have the tendency to just always insert a little bit of a literature review right into my workflow. And that's where I'll hit up stuff on Medium, like, hey, I'm trying to do this thing. And the next thing I know, pops out an article, and someone used a library I never heard of to like do it way faster than the way I had done it previously.
Like I hadn't used that Y finance library because I don't really work with stock data. We just chose it for this workshop, and I had Googled like how do you get stock market data easily or something like in Python, and that library popped up. So that's usually I'm trying to like do something, and then that's how I learn about the library.